So let's remind ourselves of what we were talking about last time. What was last week all about?
Propositional logic.
Propositional logic. Propositions. What's a proposition?
It's a statement. It's either true or false.
It's something that's either true or false, not both. If I tell you alpha is a statement, you instantly know it's either true or it's false. Now, we're going to use the words statement and proposition interchangeably in this course. For the sake of this class, they're the same thing. So a proposition or a statement, it's a sentence that is either true or false, not both. Pretty straightforward, right? And then we went over our five, well, first off, so we've got two statements here now. I have the statement alpha, the statement beta. Two statements, right? With two statements, we have four possible combinations of values. It could be the case that alpha and beta both happen to be true statements. It could be something like today's Monday and the sky's blue. Those could be my two statements here. In that case, they'd both be true statements, right? It could be the case that alpha is a true statement and beta is a false statement, right? It could be the case that alpha is false and beta is true, and then it could be the case that both my statements were false. Those four possibilities are the only four possibilities. Because alpha and beta represent statements. They have to be true or false. Good so far? And then we introduced you to the five basic symbols that we're going to be using in propositional logic. The first one was this line with a little dash at the end. What does that mean? Not. So if alpha is true, not alpha is false. And again, if alpha is true, not alpha is false. If alpha is false, not alpha is true. If alpha is false, not alpha is true. So, depending on your alpha value, here's your not alpha value. And similarly for beta. Tell me what's right here.
False.
We're going to go like this. We're going to start with you, then 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 you. You're going to tell me the square that we're on. All right? So starting with her.
False.
True.
False.
True. Oh, sorry.
Remember that symbol? And. So true and true is?
True.
True. Good. True and false?
False.
False and true?
False.
False and false?
False. Or true, sorry.
False and false is false. I tell you, I'm a billionaire and I'm 10 feet tall. Did I tell you the truth? No, if I tell you two false statements and I add them together, it's false. A false statement, false. Okay. I think we're back around to you.
True.
True or true is? True.
True and false is true.
True. False or true is?
It's or.
That's an or. Oh, sorry. So we did and, now we moved on to or. Good. So false or true. False or true is?
True.
True. False or false is?
False.
False. Good. All right. The hard ones now. Implications. That arrow means implies. All right. So true implies true is?
True.
True. Good. True implies false is?
True implies false is false.
Is false. If I'm holding a piece of chalk, I'm 20 feet tall. Is that true? No. Okay, false implies true is?
True.
This is the hard one. True, vacuously true. And false implies false is?
False.
True, vacuously true. Anytime your antecedent is false, your whole implication is true. Now, unfortunately, last week I skipped a slide on vacuously true statements somehow. I don't know how I did that. So we'll go and we'll cover that better today. So that's understandable if you get confused on those two. And then finally, we had logical equivalence. What does it mean for two things to be logically equivalent?
They have the same truth value.
They have the same truth value. So, if alpha is true and beta is true, do they have the same truth value?
Yes.
Yes.
True.
Yes. If alpha is true and beta is false, do they have the same truth value?
No.
No. If alpha is true, if alpha is false and beta is true, do they have the same truth value? No. And finally, if they're both false, do they have the same truth value?
Yes.
Yes.
Yes. Okay. That was going over our five basic operators. That's the heart of propositional logic right there on that table. You got the heart of it. Okay. Now we proved some theorems last time. we proved how to distribute a not over an and how to distribute a not over an or. For example, when we said, if I say today's Monday and it's hot outside, and now we try and negate that, what does that mean? It means either today's not Monday or it's not hot outside. You remember that?
Yeah.
Similarly, if I say that dish comes with super salad, and now we try to negate that, what does that mean? It means that dish does not come with soup and that dish does not come with salad. Coming back to you? So this is now symbolizing those two facts. So again, we have alpha and beta, all our possible combinations of value. True, 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 false, false, true, false, false. Won't make you redo that. All right. Now, alpha and beta. So alpha is true, beta is true. Alpha and beta is true and true is
True.
true. Now negate it makes it false. So we're going to work from inside outwards. All right. True and false is
False.
false. Now negate it.
True.
False and true is
False.
now negate it. Does everyone understand what we're doing? So on this next one, we're plugging in false and false for alpha and beta. False and false is
False.
now negate it makes it
True.
true. Okay. Now let's look at not alpha or not beta. So if alpha and beta are true, we're looking at false or false.
False.
Everyone understand what we're doing? Okay, so false or false is?
False.
Okay, now we're plugging in false or true is?
True.
True or false is?
False.
True or false is true. Or it just means at least one of them has to be true. If I say your food comes with soup or salad, and it came with soup and not salad, did I tell you the truth?
Yeah.
And then finally, true or true is
True.
good. And we see they gave the exact same truth values regardless of what alpha and beta were. Regardless of if they were true or false, these always spit out the same value, so they're logically equivalent. Let's do the same thing over here. True or true is
True.
true. Now negate it makes it
False.
true or false is
True.
now negate it makes it
False.
false or true is
True.
and then negate it makes it
False.
and then finally false or false is
False.
and then negate it makes it
True.
okay. Now our last one here. False and false is
False.
false and true is
False.
true and false is
False.
true and true is
True.
and once again they give the exact same thing. Yay. Any questions on those ones? Okay. And then finally, our implication. So rewriting out our implication here. So same thing we had up here. Alpha and beta, two statements. You can have true, 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 false, false, true, false, false. Implies, we already did right here. So just taking that column and sticking it right there. With me so far? Now we went over what it's called when we swap our antecedent and conclusion. What's it called when I flip those positions? What's this one called?
Converse.
The converse. The converse of the implication. So if this is an implication, this is its converse. You swap the antecedent and the conclusion. You swap your alpha and your beta positions. Make sense?
Yep.
Okay? And now, let's write out the converse really quick. So this time we're doing beta implies alpha. So true implies true is
True.
true. False implies true is
True.
false implies true is
False.
false implies true is
Vaccuously true.
vacuously true. You were right the first time. Repeating's not an argument.
Oh, my bad.
You don't change your mind because I say a question again. Keep thinking. All right. False implies false is, or sorry,
True.
true implies false is,
False.
False.
and then finally false implies false is,
True.
false implies false is,
Vaccuously true.
vacuously true. That's right. Okay. Now, that was a converse. Now so starting out with your implication, if I swap the antecedent and conclusion and I negate both of them, remember the name of that?
Counterpart.
That is called your contrapositive. Now notice that the converse is not the same thing as the implication. Here's your implication, here's your converse. They give you different values. Right? We're going to notice with the contrapositive, it gives us the same values. So, let's see that. So, we're doing false implies false is
Vaccuously true.
vacuously true. True implies false is
False.
false. False implies true is
True.
Vaccuously true.
vacuously true. And then finally, true implies true is
True.
true. Okay, so those were our theorems of logic that we've proven so far. Notice that this gives you the exact same values as this. So me saying, if I'm wearing shoes, then I'm wearing socks, says the exact same thing as, if I'm not wearing socks, then I'm not wearing shoes. Logically equivalent statements. Okay. So that was it for propositions. Now we move on to a predicate. Next scene, predicate. I can't remember the example I gave you. I think it was something like this. X plus or equals 5. X plus or equals 5. Is that true?
We don't know.
No?
It's not.
So is it false?
It's not a statement.
It's not a statement. It's not true, and it's not false. So it's not a statement. So this was our example of what we call a predicate. So what exactly is a predicate? It's going to sound a bit high level, or it's going to sound a bit complex language, but it's a simple idea. So what exactly is a predicate? It is a proposition valued function. That's what a predicate is. A predicate is a proposition valued function. What does that mean? If you give a predicate some amount of terms, you give a predicate some amount of terms, and it spits out a proposition or a statement. It's something that spits out something that's true or false if you give it its terms. So notice x plus or equals 5. Let's set this up. So signifying a predicate here. I'm going to call this predicate P of x. I'm saying P of x, I'm letting you know this is a predicate, and you have to give it some term x in order for it to spit out true or false. And this particular predicate is this thing, x plus or equals 5. Now, if I give it 2, then it spits out
True.
true. If I give it 1, it spits out
False.
false. If I replace my x with a 1, 1 plus 3 is
Not 5.
4. Is 4 equal to 5?
No.
No. All right, so starting here, if I plug 1 into my predicate, what do I get?
You get 4 and it's false.
So you get false. You don't get 4, you get false. It spits out true or false. Okay, if I plug 2 into that, what do I get?
True.
True. And if I plug 3 into that, what do I get?
False.
False. Wonderful. So a predicate, you give it some number of terms, and it spits out true or false. Another example. Predicate doesn't have to just take one thing, it can take multiple things. So I'm going to have another predicate, I'm going to call it T. This predicate happens to take 2 terms, x and y. X and y here are just variables. There's nothing sacred about what I put there. I could have just as easily put square and triangle, and put square here, and triangle here. I'm just telling you, these are the variables in my predicate. Okay? So my predicate T takes square and triangle, and it is square is taller than triangle predicate. Or it's taller than predicate. Right? So I plug Bob and Bill now into this predicate. Then Bob is taller than Bill is now a statement. And it's either going to be true or false, depending on who's taller. Maybe Bob's taller than Bill, then it would be true. Make sense?
Yep.
Okay. So with that, we'll get back into our slides. Move our camera over. Should turn on the projector, wasn't thinking ahead. And get record. Or my laptop. Can't really see if the camera's lined up good. Alright, that pretty much gets it. One of you want to turn off the front bake of lights? Thank you. It's right here. Sorry, Jeff.
Were you going over the Vaccuously True?
Remind me to do that at the end of the presentation. Is the internet just... There we go. Okay. So, finish a quick review of propositional logic now, moving on to predicate logic. So, predicate. What's a predicate? A predicate is a proposition-valued function of some number of variables. In other words, if you give a predicate its terms, maybe one, maybe multiple. There could be predicates that take 100 terms, there could be predicates that take 1 term. If you give a predicate its terms, then the result is a statement. Take a predicate, give it its term, that converts it into a statement. It converts it into something you can call true or false. Take x plus or equals 5, give it its term, replace that x with an actual term, like 7 there, and now it's a statement, something you can call true or false. How do you convert a predicate to a statement? Give it its terms. Potentially 1. Okay, now, predicates that happen to only take 2 terms are so ubiquitous in mathematics, we give them their own special name, and we call them a relation. What's a relation? It's a 2-termed predicate. It's just a predicate that happens to take 2 terms. Since those come up a lot, we give them their own special little name. Make sense? Okay, so examples of predicates. We have the is brown predicate. With me?
Yep.
Alright, if I throw my shirt into that predicate, it spits out
False.
false. If I throw that desk into the predicate, it spits out true. The is brown predicate. Replace the term, plug in some term for the variable, and now it's a proposition, something we can call true or false. This one, x likes y. If I plug in Jack and Jill, it spits out true. If I plug in Jack and Jane, it spits out false. Right? This is greater than 2 predicate. If I plug in 7, it spits out.
True.
If I plug in 3, it spits out.
True.
If I plug in -1, it spits out.
False.
Wonderful. And then this is the is Bob's best friend predicate. If we plug in Bill, it spits out true. If we plug in Frank, it spits out false. Good? Just predicates. Notation. For a single variable predicate, we often write it something like this. P of whatever the variable you choose in your predicate is. X or whatever. Notice all these ones I decided to use X for the predicate. I didn't have to do that. It's just standard convention. And I'm calling the predicate P. I don't have to call it P, just standard convention. So, for a single variable predicate, we may write it like that, P of X. And for a relation takes 2 terms. So, a relation is a 2-term predicate. We would write it something like that, Q of X and Y. Now, especially for the case of relations, we have a different notation we use. So, specifically for relations, it is common to write the name of the relation between the variables. So, up here, I could have said L of xy is the x likes y predicate. The likes predicate, right? It's just as valid for me to write that as x likes y. These are the same notations. L of x and y, x likes y. Make sense? And you've already used this a lot. So for example, here's a predicate you've used a lot. It's called the less than predicate. And you plug in 1 and 2, and is 1 less than 2?
Yes.
Yes, so this whole thing evaluates to true. But we never write it that way, we always write it this way, and we put the name of the predicate between them. Just as a nice convention. These say the exact same thing. You're very used to this, not so much this. So, for relations, predicates that only take 2 terms, it's very common to write the name of the predicate between the 2 terms. It's a nice convention. Make sense?
Yep.
But just convention. Alright. Now, some examples. Again, we're going to start right here. You're going to tell me, is it a predicate? Yes or no? Starting with you.
Yes.
Yes.
No.
No. What is this?
It's the same as
Jack is taller than Bill. That's a proposition or a statement. Alright, what about this?
Yes.
Is that a predicate?
Yes.
Is he telling me the truth?
Yes.
Yeah. 2 plus 2 equals 4. No, that's a statement. X loves Y? Yes. Go home.
It's not even a proposition.
No, that's a statement, right?
No.
No, what is that?
It's a
It's not a
sentence.
predicate, it's not a statement. What is
It's
it?
a sentence.
It's some collection of words. Who cares? It's not what we care about. All right. X is greater than or equal to 2? Yes. X, Y, and Z are triplets. Yes. Can you call it true?
Not right now.
No.
No, because you don't know who X, Y, and Z are. But if I gave you X, Y, and Z as 3 actual people, now you could tell me if it was true or false. So it's a predicate. This one is a predicate that happens to take 3 terms. Predicates don't have to just take 1 term, don't have to just take 2. They can take 3, 4, 5, 10, whatever. So it's still a predicate. It's something that if I replace all the variables with actual people, you could tell me now whether or not it's true or false. That's a predicate. When you plug in all the terms, it's now a statement. It's now a proposition. It's now something you can call true or false. All right. Jack is taller than X. Predicate?
Yes.
Yes. Finally, X is blue and Y is greater than 2.
Yes.
Yeah, that's the first thing is blue and the other thing is greater than 2 predicate. A pretty useless predicate. We never really want to use that in field of math, but still a predicate. Making sense?
Yep.
Not too bad? Okay. Since predicates are proposition valued, in other words, since predicates spit out propositions, we can use our logical operators, not, and, or implies logical equivalence. We can use our logical operators, not, and, or implies, if and only if, logical equivalence, to construct new predicates from existing predicates. The same way that I can combine propositions together with these things, and the result is a proposition, I can combine predicates together with these things, and the result is still going to be a predicate. That's all we're saying. So you can and 2 predicates together, the same way you can and 2 statements together, and it's still a predicate.
Gotcha.
So example, let P of X be the is greater than 2 predicate. So here's your is greater than 2 predicate. And let Q of Y and Z be the Y loves Z predicate. Then we can define a new and a fairly useless predicate. We'll call it R. We can name it whatever we want. R now is going to be the predicate we get when we and these 2 things together. I'm anding those 2 things together. So I need an X for my P of X, and I need a Y and a Z there. So R is a 3-term predicate. And what is R? It's the first thing is greater than 2, and the next 2 things love each other predicate. Pretty useless, but that's the predicate. Now, here's the predicate. What on earth am I doing with this notation right here?
Saying that it's logically
Logically
equivalent.
equivalent.
So this is how you say we're defining it in logic. I'm saying we are defining this to be this. They're logically equivalent, but that colon to the left means I'm defining something new on the left in terms of things we've already defined on the right.
Right.
And that's common notation. So when you see that little colon there, it's trying to remind you we're defining something new. So this is something we defined in terms of things we defined before. We have this defined, we have this defined, now we're defining something new in terms of existingly defined things. Just notation. Make sense? Okay. Again, give you another example. Let's assume that the less than predicate and the equals predicate have already been defined. So let's assume that those already have definitions. Now we can define a new predicate called the less than or equal to predicate, and we define it to be x is less than y or x is equal to y. That's what we mean by less than or equal. Right? And again, that's hideous notation. We hate that. We'd much rather see it this way. What do I mean by x is less than or equal to y? I define that to be x is less than y or x equals y. Make sense? Okay. So, predicates. One way that we can convert predicates into statements is to plug in our terms. Another way we can convert predicates to statements is to add quantifiers. So what are quantifiers? Don't worry, there's only 2. So today, you're pretty much introduced to 3 new things. Predicates, that symbol, and that symbol. So it's a much easier class than last time. So we're almost covered all the new stuff.
All it exists.
Make sense?
Yep.
Okay. So first quantifier is our universal quantifier. It's this upside down A looking thing. Can everyone see that okay?
Yeah.
And we typically read that as for all, for each, or for every. Okay? Next one is our existential quantifier. It's that backwards E looking thing. We typically read this as there exists. Sometimes we read it as some. Typically we read it as there exists. Alright, so going to read a statement really quick. What does this statement now say? It says, for all x, x is greater than 2. That's just reading it. For all x, x is greater than 2. Make sense? Now, question. X is greater than 2. Is that true or false?
It's predicate.
Bad question. It's a predicate. Now look at this. For all x, x is greater than 2. Is that true or false?
False.
That's false. Not every x is greater than 2. There's numbers that are not greater than 2. Notice that by adding this, we converted it into a statement. It's now something you can call true or false. Without that, you can't call it true or false. We put that on, and now you can call it true or false. Similarly, I could have wrote instead of that, I could have said there exists an x, such that x is greater than 2. So x is greater than 2, true or false? Bad question. There exists an x, such that x is greater than 2. True. Or some x are greater than 2. Two ways of reading that, we typically use the there exists. So adding quantifiers to predicates converts them into statements. So two ways we can convert a predicate into a statement. One, give it its terms. Two, give it its quantifiers. Those are the two ways we convert predicates to statements. Make sense? Okay. So, now going through. So for all x, x is greater than 2, and there exists an x. Now with the there exists, because we speak in English, and so sometimes it doesn't translate perfectly. After we read a there exists, we always just say such that. And then we read the next thing. So there exists an x, such that x is greater than 2 is the best way to read it. Make sense? And that's just a hiccup of English. Just makes it read better. So typically we write the quantifier followed by the predicate. Quantifier, then predicate. We don't put the quantifier after the predicate. We don't say x is greater than 2, there exists an x. Make sense? Quantifier comes before the predicate. Notice that while the predicate, x is greater than 2, is not a proposition, both for all x, x is greater than 2, and there exists an x such that x is greater than 2 are propositions. We can now call them true or false. We can also chain quantifiers together. So, I'm going to do some examples of just reading through statements and having you call these true or false to help you get comfortable with all this. So we're going to look at for all x, for all y, x plus y equals 0. We're going to look at for all x, there exists a y, such that x plus y equals 0. We're going to look at there exists an x, such that for all y, x plus y equals 0. And then finally, we're going to look at there exists an x, and there exists a y, such that x plus y equals 0. So reading through these, getting comfortable reading these, and tell me whether or not they're true or false. So this first one, what does it say? It says for all x and for all y, x plus y equals 0. Is that true?
False.
That is false. It is not the case that for any two numbers you choose, when you add together, they give you 0. Right? Okay. For all x, there exists a y such that x plus y equals 0.
That's true.
That one's true. What's the magic y?
The opposite of x.
The negation of x. If x is 3, the y that we use is negative 3. If x is negative 7 over 19, the y we use is 7 over 19. Right? Okay, next one. This one says, there exists an x such that for all y, x plus y is equal to 0.
No. False.
It's just the same as this one, right?
No. No.
No, they're different. This one says for every x, you can find a y such that their sum is 0. This one says there is out there some magic x such that no matter what y you choose, when you add them together, you get 0. There is no magic x out there you can find such that for all y, x plus y equals 0. So the order of the quantifiers matters. These are not saying the same thing. Make sense? Okay, so this one is false. And then finally, there exists an x and there exists a y such that x plus y equals 0.
True.
True. Can you find two numbers such that when you add them together you get 0?
Yeah. Yes.
That's what this is saying. This is saying there exist two numbers out there such that their sum is 0.
Yeah.
Okay, we're going to repeat the exact same exercise now. This time we're going to replace the plus with times, just to help you get comfortable reading these chains of quantifiers. So we're going to put times there, times there, times there, times there. Okay, for all x and for all y, x times y equals 0.
False.
False. If I take any two numbers and I multiply them together, does it give me 0? No, that's what this is saying. Let's see the next one. This says for all x, there exists a y, such that when we multiply them together, we get 0.
True.
That's true? Okay, if the x I give you is 17, what's the magic y you can multiply it by to get 0?
0.
0. So for every x you choose, there exists some y such that their product is 0. That's true. Next one. There exists an x such that for all y, their product is 0.
True.
True. This time there is a magic x. What's the magic x?
0.
0. 0 is a magic x such that no matter what y you choose, their product is 0. So in this case, this time this one came out true. And then finally, there exists an x and there exists a y such that their product is 0.
True.
True? Okay.
Yes.
Yeah. Can you find two numbers such that when you multiply them together you get 0?
Yes.
Okay, that's all that's saying. Getting comfortable with these? Reading them? Okay. So that is quantifiers and showing you that the order you put quantifiers in matters in chaining quantifiers together. So I showed you statements with one quantifier. All those ones we had two quantifiers on it. There's no reason you can't have statements with 27 quantifiers. I've never worked with one like that, but there's no reason you can't have them. All right. So we did those examples. Next. Okay. So now let P of x be a predicate, any predicate. Then for all x, P of x is a proposition. So far I was trying to get you comfortable with the fact that this is a proposition. That this is something we can call true or false. And so far I've been trying to get that to appeal to your intuition. But how exactly do we know how to call this thing true? And how exactly do we know how to call it false?
You're going to define it like that.
We have to define it. We have to define when it's true and when it's false. So far we've been relying on your intuition. Now we actually need to define these symbols. Define that statement. How do I know when that's true and when that's false? Make sense? Now we're in trouble here because we can't always just do a truth table like we could before. Because x could possibly take in infinitely many things. And so I can't write out a truth table with every possible number, plugging it into the predicate and saying this one came out true, this one came out false. That would give us an infinite definition. So we can't just use a truth table. Right? So we have to use a bit more high-level language. So let P of x be a predicate. Then the statement, the proposition, for all x, P of x is a proposition. And it is true. What does if with two f's mean?
If and only if.
If and only if. So it's a proposition that is true if and only if P of x is true independent of x. Otherwise it's false. So if P of x is true regardless of what you choose for x, then we say for all x, P of x is true. If P of x is not true regardless of what you choose for x, then we would say for all x, P of x is false. Let's give you two examples. I tell you x is greater than or equal to x. There's our predicate. Is that true regardless of what you choose for x?
Yes.
Yes, no matter what x you choose, x is always greater than or equal to itself. Because it's equal to itself. So in this case, for all x, x is greater than or equal to x is true. Because it's true independent of what we choose for x. On the other hand, For all x, x is greater than or equal to 2. Is this true independent of what we choose for x? No, there's some x out there that we could choose that makes us evaluate to false.
Right.
Okay, so that's its definition. Now, we've got to define this thing, when this thing is a statement. I'm going to give you its definition just for the sake of giving you its definition. And if this is over your head, that's okay. Those of you who want everything complete and self-contained, here it is. So let P of x be a predicate. Then we define there exists an x such that P of x. We define that to be, it is not the case that for all x, you don't have P of x. That's its precise definition. Now let's focus on intuition. Let's pick a predicate for P. Give me a predicate.
X plus 4 equals 6.
That's a statement. Oh, x plus 4 equals 6. No, you're right. Sorry. X plus 4 equals 6. So there's our predicate P. Now, we're saying that there exists something out there such that x plus 4 equals P. This is saying it is not the case that no matter what you pick to put in there, it is not equal to 6. This says there is something out there, there is some x such that x plus 4 equals 6. This says it is not the case that for all x, when you plug it in there, you do not get x plus 4 equals 6.
Oh.
Who are we missing?
Samantha.
Samantha.
Okay, thank
Yep.
you.
That makes sense. Okay.
Let's try it in some different language. This could be, there exists a white swan. Then this is saying it is not the case that every swan is not white. There is a white swan. It is not the case that every swan is not white. Those are saying the same thing.
Yeah.
There's the intuition, and then there's a precise definition if you want the precise definition. You don't have to work with that definition directly. So, that's the example I gave here. Examples of reading this, that left one says, there exists a swan such that it is black. Says the same thing as, it is not the case that for every swan, it is not black. Say the same thing, just reading those out. Okay. In general, there exists an x such that P of x says the same thing as, it is not the case that for every x, not P of x. Good? Okay. Now, with this definition, we're going to see how to start coming up with the negations of statements. You've already been doing this. You've already got good intuition for this. We've already done, I would tell you something like, all men in Georgia are at least 6 feet tall. And you were telling me last week the negation of this. What would you say?
Not all men in Georgia are at least 6 feet tall.
Not all men in Georgia are at least 6 feet tall. That's one way to say it. And some men in Georgia are not at least 6 feet tall is another way to say that. I'm going to show you how to get that from this notation now, to just calculate that. So, if P of x is a predicate, then for all x, P of x, let me see back over here really quick. I'm not going to prove any of these three. I'm kind of tempted. Let's not do it. Okay. I'm not going to prove these three. We're just going to give you the language for it. Using the definition that we have right here, this definition, it's not too much work to prove each of these three things. But it's a lot of symbols, and I don't want to scare you with the symbols. And since we're just going to be showing you this and then moving on, I don't want to dwell too much on it and have you perfect this. Unfortunately, it's not a full logic course. Okay. So here's 3 theorems. Here's things that we could prove with that definition, but we'll try and connect the intuition in your head. P of x, if P of x is a predicate, then for all x, P of x is logically equivalent to, it is not the case that there exists an x such that not P of x. Let's pick our predicate. We'll pretend like our domain is swans, and we'll do the P is black predicate. So this is saying for all swans, they are black, or every swan is black, is the same thing as it is not the case that there exists a swan that's not black. all swans are black, it is not the case that there exists a swan that's not black. Make sense? Okay. Now, you can see how you would quickly get this from this, just negate both sides. And the negation of a negation cancels out. We didn't prove that, but not alpha is logically equivalent to just alpha. Two negations cancel out.
Makes sense.
So take this, negate both sides, negate that side, and you're left with this now. That negation's there, those two negations cancel out. So that's a quick way you could write that from that. But let's see what this says. It is not the case that every swan is black is logically equivalent to there exists a swan that's not black.
Yep.
Not all swans are black says there exists a non-black swan.
Yep.
They'll say the same thing. With me? And then finally, it is not the case that there exists a black swan says that for all swans, they're not black.
Right.
It is not the case that there exists a black swan says the same thing as for all swans, they're not black. Now, focusing on these two theorems here, these tell us how to distribute a knot over a quantifier. If you've got your knot over here, and you want to get it inside, I want to distribute it inside and apply it to the P, it converts a for all into a there exists. You see that? Similarly, not there exists P of X is the same thing as if I want to take that knot and put it in here with the P, it converts the there exists into a for all.
Right.
Make sense? And now, when you get comfortable with this stuff, this is what everyone is doing in their head. When you know logic, these are the two things you're thinking in your head when you look at statements like this. All men in Georgia are at least 6 feet tall. What's that saying? It's saying for all X, being tall applies to X. That's what this says, right? And now we want to figure out how do we negate this? What's the negation of that?
There exists an X.
When you negate a for all, you convert it into a there exists, and then you can put the not inside. So if we're trying to say not all men in Georgia are at least 6 feet tall, that's the same thing as there exists a man in Georgia, such that he's not 6 feet tall.
Yeah.
At least 6 feet tall, wherever the predicate is. Let's do that again with this next statement. We're going to start by symbolizing it. Every rectangle is a square.
For all rectangles, they are squares.
Every rectangle is a square. So let's start with how would we symbolize that?
For all.
It's a for all. For all X.
Being square applies to X.
Being
That's-
squared
yeah.
applies to, or, right,
For all X.
yeah.
So this one, we've got a little bit of a compound going on inside. We're saying if you are a what, then you're a what?
If
Rectangle
you're a
is-
square, then
If you're a rectangle,
you're
then you're
rectangle,
square.
you're square.
If you're a rectangle, then you're a square. Being a rectangle applying to X implies being a square applies to X.
Gotcha.
That's what this says.
Gotcha.
Now I want to negate it.
There exists a rectangle that is not a square.
So that would say that there exists an X such that we have to negate this whole thing.
Your knot shouldn't be there.
Oh, thank you. So now we want to negate this. If we're going to negate this, we're going to write that down here. Now I have to negate this whole thing. And I realize that there's one more theorem I forgot to show you. So it's a good thing we did this. The last way you can think about alpha implies beta is, let's see if I don't go too far this way. I think I'm still on the camera. So we've got alpha, we've got beta, we've got alpha implies beta. It turns out that that's the exact same thing as not alpha or beta. So let's quickly do this. True, true. If alpha is true and beta is true, true implies true is.
True.
And now false or true is.
True.
All right, next, true false case. True implies false is.
False.
False.
False. False or false is.
False.
False. Okay, now we can do the false true case. False implies true is.
True.
True or true is.
True.
And then finally we can have false, false here. False implies false is.
True.
True or false is.
True.
And look at that, these give the exact same things. So, before we distribute the negation, so we're trying to figure out the negation of that. Well, that's the same thing as the negation of, for all x, we either have not r of x, or we have s of x. This is the same thing as that, because implies is the same thing as not alpha or beta. So I just replaced the implication with the not the first thing or the second thing. You with me? Okay. Now, I'm going to take the not inside. So that turns my there exists into that. I'll use square brackets here, put our not here. And now we've got to not this whole thing. Not r of x or s of x.
Yes.
Right?
Or it's or not s of x, right?
No.
Distribute.
The not only applies to the first term.
Oh, I see. Okay, never mind. Yeah, two.
So far we just put the not inside. We haven't distributed it yet. Now finally we got to distribute this not over an or. How do you distribute a not over an or? If you distribute a not over an or, it converts it into an and. And so finally, distributing that not over it, I get there exists x such that not r of x is the same thing as
R of x.
r of x. When we negate over an or, it turns it into a, and then not s of x is not s of x. And there it is. So here is now the negation of this. Every rectangle is a square. There exists something out there such that it's a rectangle and not a square.
Yeah.
There's something out there that is a rectangle and not a square.
Yeah.
Now, with these simple statements, it's easy enough that your intuition can just think about it. But here is just using the rules exactly
Gotcha.
and not relying on your intuition. Okay. Let's do another one. Every circle has a center. How do we symbolize that?
For all x.
For all x, where x could represent a circle in here,
The predicate circle applies to it.
having a center applies to it. So it's understood that our domain here is circles. We won't focus on the domains because that'll get confusing.
Okay.
So for all x where x is a circle, it has a center. What would the negation of that be now?
There exists a.
So we want to figure out the negation of that. When we distribute the not over for all, it converts into a
There exists.
there exists. So there exists an x such that not having a center. There exists a circle such that not having a center applies to the circle.
Yeah.
Make sense? Okay. Here's the last one we'll write all the way out. For every pair of numbers a and b, a plus b is equal to b plus a.
For every a.
Okay. So now we're going to say what?
For all a.
For all a, for all b, this one's going to have two quantifiers. Right?
Yes. Question. Can you write that for all a comma b, or do you have to have two quantifiers?
We'll leave it as separate quantifiers for now. We won't go with nice hands for how we deal with these things since we'll be done with them here in a sec. This is just to expose you to predicate logic so that you know it's a thing and know it exists. And get you comfortable with, you can actually think about exactly what the English sentence to say, and then we're going to move on. So, won't focus too much on that. So for every pair of numbers, a and b, a plus b equals b plus a. So we need the equals predicate here. We'll call it equals. Applies to a plus b and b plus a. Those will be the two terms that we plug in. Or, if we just want to call this, let's not write it out that nicely. Let's just call this whole predicate here. We'll just call this, we'll call it a capital E, is equal when you sum them for a and b. So we'll call that whole predicate just that thing. So we'll call this the E is equal when you sum them both ways of a and b, is the name of that predicate. Okay. Now we want to negate this, right?
Yes.
So how are we going to do this?
When you
There exists an A and there exists a B.
Is it going to be there exists both? So here's the trick. When we distribute that over, it's going to turn this into there exists and pop all the way inside.
gotcha.
So it doesn't go over the entire thing. So it's going to turn into there exists an A for all B. It is not the case that E, A, B. Oops. Give me more space down here. So for every pair of numbers, A and B, A plus B equals B plus A, what does your intuition tell you it should be?
There exists a pair of numbers A and or there is
Oh.
there exists a pair of numbers A and B such that A plus B is not equal to B plus A. Okay.
Yeah,
that's what
Follow your intuition. Good.
Alright.
That's what I was saying.
Okay, okay. Okay.
There we go.
Makes all sense.
So we're negating this for every pair of numbers A and B, A plus B equals B plus A. The negation of that is there exists a pair of numbers, there exists an A and there exists a B, such that it is not the case that A plus B is equal to B plus A.
Right.
Make sense?
Yep.
Okay, and so there you go.
Okay.
That's how you distribute it over. That's how you use these things. That's what predicates are. That's what quantifiers are. And that's how you can go through negating these. These ones should be easier to negate. I think that we've done the hardest one. Make sense?
Yeah.
So you will never on your homework be required to actually symbolize it this way. If you get used to symbolizing it this way, it'll help a ton. And you'll completely understand exactly what these statements are saying. If you know how to symbolize them, you are so well off, it's ridiculous. That shows such a fantastic understanding of what is being encoded in some statement. So fantastic practice if you can handle it. Okay. So that's the new stuff. Now we're just going to introduce concepts of proof. So every field of mathematics is simply determining the logical implications of the given field's axioms. Pick any field of mathematics out there. Algebra, geometry, topology, doesn't matter what it is. It has what we call its basic axioms or its basic assumptions. And it's going to have some number of them. I can't remember how many axioms we have in our class. I think we have like 10. So we're going to have 10 initial statements that we start with. Our whole goal from there on out is to see if those 10 statements are true, what else is true. Let me introduce you to a stupid simple axiomatic system. We're going to call this axiomatic system Bob. In Bob, we only have two axioms. Axiom 1, which we'll call A1. Axiom 1 will be all men are mortal. Axiom 2 will be Bob is a man. So here are our only two axioms, right there, for this whole system. Now notice that if you know all men are mortal, if you know Bob is a man, what do you know?
Bob is
Bob
Bob.
is-
So these two things together imply Bob is mortal. This is what we mean by a theorem. A theorem is something that is ultimately proved from your axioms. Now this is a stupid simple system that only has two axioms. And we only have one theorem we can prove. Okay, that's a pretty garbage system of math. It's a system, it works. Nothing wrong with it. But not very useful. So in our system, we're going to have 10 of these initial statements instead of 2. That's what we're going to have. And then we're going to start looking at them. We're going to start asking ourselves, well, if these two are true, what does that mean? And these two together are going to imply some new statement that we call a theorem. And maybe these two together imply some statement that we call a theorem. And then maybe this statement that we have over here and this one together imply some theorem. And maybe taking into account this statement, this theorem, and this theorem, they all together imply some new thing, some theorem. And it's building out this web of implications. That's what geometry is. That's what every systematic body of knowledge is. If we were in Newtonian mechanics, our 3 axioms would be Newton's 3 laws. If we want gravity, we'd introduce Newton's 4th law, law of gravity. And Newtonian mechanics, classical mechanics, basic physics course, is looking at the logical implications of those things. That's what it's doing. We're in geometry, so we're going to be looking at geometric axioms, geometric postulates. Postulates, axioms, same thing. I might use those words interchangeably. And whatever they imply, whatever they entail, we call theorems. So what do? We just set up some set of premises, some set of postulates or axioms, and we just start seeing if they're true, what else is true. And we call it theorems. And that's what math is. That's it. That's what we're going to be doing in this class. Pretty simple, right? How could math ever be hard? Okay. So how do we know when we've proven it? So every field of mathematics is simply determining the logical implications of the given field's axioms. If we're in Bob, our two axioms were all men are mortal and Bob is a man. All proofs are just demonstrating that given some set of assumptions, some conclusion follows. We show that these two things together imply some conclusion. That's what a proof is. We show that it follows. There's three common proof styles that we have. What we call direct proof, proof by contrapositive, and then proof by contradiction. These will be the three most common styles of proof. How do these work? If you know alpha, and you know alpha implies beta, then you must know beta. If you know that alpha is true, and you know it's true that alpha implies beta, then you must know beta. What does this mean in symbols? It means alpha and alpha implies beta, these two things together imply beta, is a tautology. This is always the case. If you know alpha and you know alpha implies beta, then you know beta. This is always the case. If we were to write out the truth table for this, in this one's column, it would be true, 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 true. It would always be true. It's impossible to make this thing right here false. This is what we call tautology. So it's always the case. If you know alpha, and you know that alpha implies beta, then you know beta. You want to see the truth table for this? We'll do the truth table for this one. We won't bother with the next two. How about that? Just to give you a sense of what we're saying here. So I've got two statements. Alpha. We've got alpha. We've got beta. We'll be looking at alpha. Alpha implies beta. We'll be looking at alpha and alpha implies beta. And then finally we'll be looking at alpha and alpha. Why do I keep doing A's? Alpha and alpha implies beta. If you know those two things together, then it implies beta is always the case. Okay, here's the truth table we're writing out. My claim is that this one's column is going to be all truths. So let's see that. First off, we put true here, true here. True implies true. True. True and true. Remember, this piece is just this column. So true and true is true. Okay. Now this is doing this implies this. True implies true is true. Okay, first case came out true. Good. Okay, now we're doing true false. True implies false is false. Now we're doing false and false. True and false is false. Okay, finally, we're doing false implies false. We're doing this implies this. False antecedent implies conclusion. False implies false is
True.
Vaccuously true. Okay, so far, true, true. Next one, we'll put the false here and the true here. False implies true is
True.
true, vacuously true. Over here, we have true and, we have false and true is
That's false.
false and true. We've already evaluated this thing, and it's just true. Good. Okay, so false and true is false. Now we're looking at this column implies this column. False implies true is vacuously true. Next one. We put a false here and a false here. Okay, false implies false is false.
True.
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 True. Okay. Next we have false and true is
False.
false. And then finally we get false implies false is
True.
true. So no matter what you plug in for alpha and beta here, you cannot make that thing false. It's what we call tautology. And so it's why it works as a method, a rule for proving things. Here's your rule for direct proof. If you know that alpha is a case, and you know that alpha implies beta is a case, then you are guaranteed that beta is a case.
Yes.
If alpha is true, and alpha implies beta, then beta. I'm just reading this sentence. This always implies this. Make sense? So that is one way that we prove things. Oops. Not going to the next slide. I meant to turn this back on. Okay. So that style of proof is what we call direct proof. So if you know alpha, and you know alpha implies beta, then you know beta. In symbols, it's that thing. Next. If you know that not beta is true, or in other words, you know beta is false. If you know not beta, and you know alpha implies beta, then you know not alpha.
It's the contrapositive.
Through the contrapositive, because remember, alpha implies beta is the exact same thing as what?
Not beta implies not alpha.
Not beta implies not alpha. So if I know not beta, and I know not beta implies not alpha, then I know not alpha. If I know not beta, and I know not beta implies not alpha, then I must know not alpha.
Yes.
Make sense? That's called proof by contrapositive. Now, proof by contradiction. If I know that alpha implies a statement that is for sure false, if I know that it's true that alpha implies some statement that's false. So if you know that alpha implies false is true, in other words, alpha implies false is a true statement, then you know alpha is false.
Yes.
In other words, if alpha being true entails something that's impossible, alpha must be false.
Yes. Yes.
If alpha being true implies something that's impossible, something that's for sure false, then alpha must be false. Because if it were true, then we get something that's impossible. Make sense? Okay, so those are our three styles of proof. And you'll see examples of all of them as we go throughout this course, but essentially you'll be doing one of these three types of thinking for most of your problems early on. So let's go through some examples using some of these. So you got some notes in the mail. It says, if it rains on commencement day, then graduation ceremony will be held in the gym. If it rains on commencement day, the graduation ceremony will be held in the gym. What's alpha?
It rains.
It rains on commencement day. What's beta?
All the ceremonies.
Ceremonies in the gym. Okay. So today is commencement day, and it's raining. So I know alpha is true.
Yes.
So what do I know?
Beta is true.
Beta is true, or in other words, a ceremony will be held in the gym. So you get a notice in the mail. It says, if it rains on commencement day, then the graduation will be held in the gym. You know alpha implies beta. Commencement day comes around and it's raining. You know alpha is true. Put those two things together and what do you know?
Means that beta is true.
Beta must be true. It's going to graduation ceremony will be held in the gym. Go ahead.
So if alpha is true and beta is not true, then you know that alpha implies beta is not true. But does that
Correct.
mean that you think of alpha as not true?
Well, you're just expressing a relation between those. What we're saying is that if you know that alpha is true and you know alpha implies beta is true, if you know these two things, you can conclude beta must be true. That's what we're saying here. Now, if you know beta is false, then you know that alpha can't imply beta if alpha is true. Okay. So, setting up our next one. Jim claims that negative 3 is the root of the polynomial x squared minus x minus 6.
Yeah.
My changes were not saved. Oh, they were. I just didn't have a wire here. This is supposed to be y equals x squared minus x minus 6. Sorry. Ignore that one. Okay. Jim claims that negative 3 is a root of this thing. What does that mean for it to be a root of it? It just means when you plug it in, it makes it 0. If I plug in negative 3 for x, it'll make it 0. That's what Jim's saying, okay? So if negative 3 is a root of that, then it's true that when you plug it in, it's 0. What is alpha in this case? Alpha is negative 3 is a root.
Root.
Root. Thank you. That's what alpha is. Beta is that when we plug in negative 3, we get this. Beta is negative 3 squared minus negative 3 plus 6 equals 0. Sorry, we won't put equals here to not get confused with that. Alpha is this thing, beta is this thing. Okay, so what did we tell you? So I'm telling you alpha implies beta is true. It is true that if negative 3 is a root of that polynomial, then this is the case. That's true. So we know alpha implies beta is true. You with me so far? Now, let's look at beta. Is beta true? What's negative 3 times negative 3? 9. Take away negative 3 gives you 9. Take away negative 3. Not take away 3, take away negative 3. Is the same as adding 3 is 12 plus 6 is 18. That's not close to 0. So beta is false. Or in other words, not beta is true. So we know alpha implies beta, and we know not beta. And so from that, we can conclude not alpha. Or in other words, negative 3 is not a root of that polynomial. So that would be a proof using the contrapositive. Because alpha implies beta is the same thing as not beta implies not alpha. So we don't want to think about it as alpha implies beta. We want to think about it as not beta. Not beta implies not alpha. These two say the exact same thing, right? Yes. Okay, there's an example with each of those. Okay, last thing we got introduce, identity, and then we'll go back and do vacuously true. So far, I've been just using equals however I want, willy-nilly. Equals is a very special symbol. It is not a symbol of mathematics, it is a symbol of logic. It's more foundational than mathematics. It's not like plus and times. Those are symbols of mathematics. Equals is on a more fundamental level. It's like and implies and ors. So equals. Equals means that whenever you talk about it, it's given its meaning by the law of identity, which can be split into these two rules. So what's the law of identity? The law of identity is that everything is identical with itself. Everything is identical with itself. It's often summarized as A is A, or A equals A, or to put it precisely, what does it mean? It means for all x, x equals x. No matter what you choose, everything is always equal to itself. That's the first part of the law of identity. The second part of the law of identity, often called the principle of extensionality, doesn't matter if you remember that or not, it just means equals may be substituted for equals. And these are the only two rules governing identity. Everything is identical with itself, and equals may be substituted for equals. With that, we're going to do a proof. I'm going to prove to you that if A equals B, then A plus C equals B plus C. So here we're going to do our first little proof. So I'm going to prove, give you all my notation for how I write this. If A equals B, then A plus C equals B plus C. Here's what we're proving. Maybe just get rid of this so we have as much space as we need. Okay. What's my antecedent? What's my alpha?
A equals B.
A equals B. Here's our alpha, A equals B. What's my conclusion?
A plus C equals B plus C.
This piece. There's our beta. I need to show that if alpha is true, then beta is true. That's what we're trying to prove, right? Okay. The way you prove an implication is you assume the antecedent and show that implies a conclusion. I'm going to show that if this is a case, then that is a case. So you always start, not always, but very standard thing to do in proofs is to start by just saying 1, assume or let whatever your alpha is. So I'm going to start this blindly without even thinking. I'm just going to say assume A equals B. Step 1. Now I need to show that somehow leads to this thing being true. Okay. 2. I know that A, let's see how I want to say this. Observe that A plus C is equal to A plus C. How do I know that that's true?
Because of your
Because
law of
of
identity.
Law of identity. Everything is identical with itself. I have the exact same symbols over here that I have over there. It doesn't matter that you even know what those symbols represent. If you have the exact same symbols on both sides of your equalities, you're good. Everything's identical with itself. So we know that from law of identity. Okay, number 3. Now, remember the law of identity had 2 parts to it. Everything's identical with itself and equals may be substituted for equals. I can substitute equals for equals. So I can replace this A with a B, and I'm not cheating. So then, A plus C is equal to, equals may be substituted for equals. And again, I get that from identity. Right? Sum 4. We're done. Therefore, A plus C is equal to B plus C. And then you put a little box at the end of your proof.
Thank you.
Huh? And that little box signifies that you're done. You used to put QED at the end of it, and it was some Latin phrase, shorthand for some Latin phrase, and thus it is demonstrated. And now we just put a little box at the end. Means, and thus it is demonstrated. We've proven it. There's your first proof. Pretty standard proof, pretty straightforward proof. This is what you will be required to do a lot of in this class, a lot of proofs. And unfortunately, there's a lot of style to proofs. There isn't, here's the hard, fast rules for how exactly you go about proving things. Your author of your textbook is trying to push you towards 2-column proofs, where you give your proof and then you give the reasoning. So we would have put the identity in the right-hand column. If you see what he's saying there and you want to use those types of proof styles, that's perfectly fine. You can use 2-column proofs if you want, or you can write it out like I'm writing it out and just state the rule you're using as you go. As long as it's clear to me and it's clear to Bob what you're doing, anyone else in this class can understand what you're doing, then you're good. A common rule of thumb when you're writing a proof is write it so that someone else taking the class with you could know exactly what you were doing. Standard rule of thumb. But so there's our first proof. Okay. So we just rightly proved if A equals to B, then A plus C equals B plus C. Now, I shouldn't have erased my proof, but there was nothing special about equals in that proof. It's also the case that if A equals B, then A times C equals B times C. Okay, I just did the scratch work for this proof on the side. So just doing the scratch work this time, not doing it very thoroughly. I say 1, so we're proving this one. Let A equal B. 2, what do I know? I know that A times C is equal to B times C. How do I know that? Identity. I'll just put an I on the side for identity. Don't be as lazy as me. 3, then I know that A times C, A times C is equal to A times C, sorry. Everything's identical with itself. That's using law of identity. And then A times C equals B times C. This is using the second part of law of identity. So we'll call it I2 and I1. I1 and I2 for each of the parts of identity that we're using. And that's done. And again, there's nothing special about times. We didn't use any information about the time symbol in there. Pick any operation you want, as long as it's well defined. We'll call it star.
What do you mean by well defined?
Huh?
What do you mean by well defined?
you can't accidentally be dividing by 0 in here or something. You can't break the system you're talking about. But put that aside for now. The point is, we now know always and forever, if A equals to B, and whatever, I use a start here, but whatever, fill in the blank, is an operation where that and that are well defined in your system, then always and forever, if A equals B, then A operation C is equal to B operation C.
Right.
Now, you've been told this over and over again in your math. What you do to one side, you have to do to the other. Here's the rules you were actually using. Here's the logic that lays behind it. You were actually using the law of identity. Okay? Any questions there? So that's it for new material today. Oh, let's go back now and talk a little bit about vacuously true. It's not really it's more just for fun than it is a heavy-duty thing. Was that it? Vacuously true. Okay, so here's what we missed last week. So, going back, talking about implications. If then is not the same thing as if it was the case that, then it would be the case that. So here's one of the ways that people have a problem thinking about vacuously true statements. Is you want to interpret this the same way you interpret that. Let me give you an example. If there are 100 husbands in America, then there's only one wife. This is a true statement. Are there 100 husbands in America? This means exactly. Are there exactly 100 husbands in America? No. So this is false, implies, who cares? False implies anything is true. You naturally want to think about this as, if it was the case that there were 100 husbands in America, then it would be the case that there's only one wife. You want to take your system and you want to say, okay, now everyone start moving around, let's keep going until we've only got 100 husbands here, and then check and count the wives. Which is not what it's saying. Those are two very different things. You've got to think about, when you think about implication, think about it as just the state of the universe, as it is now. You don't get to change the system and say, well, if I would change it this way. No, that's not what we're talking about. So here's one natural way that you want to interpret if-then, which can get you in trouble with vacuously true statements. There's one warning. Now, one more thing to get you with vacuously true statements. Sometimes you can... The reason that false implies anything is always true is because if you allow one false statement into your system, you can now prove anything. So I'm going to give you an example. I'm going to prove to you that if 1 is equal to 0, that's a false statement. But if we allow that false statement into our system, I can now prove anything. I can prove I'm the Pope or any other ridiculous thing you want me to prove, as long as you allow 1 to equal 0. Or if you were to allow -5 to equal 19, I could still do the same thing. It doesn't matter the false statement you give me. If you give me a false statement, a lot of times I can come up with a constructive proof to prove any absurd thing you want. So I'm going to walk you through this example. If 1 is equal to 0, I'm the Pope. You ready for this? The Pope and I are...
1.
How many people are we?
2.
2.
The Pope and I are 2. Right?
Yes.
But, so 2 is equal to 2. Now I'm going to subtract the same thing for both sides. So then 2 minus 1 is equal to 2 minus 0.
Right.
Because 1 and 0 are the same thing. What's 2 minus 1?
1.
1. What's 2 minus 0?
2.
2. So the Pope and I are 2. Therefore, the Pope and I are 1. Therefore, I am the Pope. There you go. If you allow any false statement into your system, you can prove anything. That's why having a false antecedent always entails a truth.
Right.
Make sense?
Yes.
So there's the intuition there. So vacuously true. An implication is vacuously true provided the antecedent cannot be satisfied. It cannot be true. It's false.
Gotcha.
Make sense?
Yes.
So that's vacuously true. Okay, so that's it for lecture. Any other questions? Go ahead.
Will you leave it up for a second so I can write down the definition?
Oh, sure. Any other questions? All right, so then we'll stop the recording and we'll move on to homework.